we are talking about quadratic functions. And I want to start with a little refresher of what we saw with linear functions and exponential functions. Remember, three big types of functions that we see in Algebra 1, linear, exponential, and quadratic. We've seen linear and exponential already. Okay? So on the first page of our new set of notes, we've got a table of values here, x by table, for a couple different functions. I want you to take a look and see which of these are linear and exponential. Now, remember, linear functions either add or subtract the same number from that y value each time. So as we move down our y list, I want to know, am I adding or subtracting the same number each time? Important to note that my x's are increasing by 1 each time. If my x change wasn't consistent, it would be more difficult to see what that y change is. Since it's the same each time, this shouldn't be too bad to see that change in y. And then exponential functions, those ones that we just looked at, I'm multiplying or dividing by the same number each time. So I want you to take a look at our three tables here. Find the linear and exponential functions. Which of these are linear functions? The first one is a linear function. If I look at the y values, to get from 0 to 5, I have to add 5. To get from 5 to 10, I add 5. To get from 10 to 15, we add 5. We're adding 5 to that y value each time. So what would be our next term? 25. Which of these are the exponential functions? The next one, that middle one, is an exponential function. So if I look at the y's, to get from 3 to 6, we could add 3, but we could also multiply by 2. And importantly, to get from 6 to 12, I could multiply by 2. So I want the option where I can do the same thing each time. So I can multiply by 2, multiply by 2. To get from 12 to 24, we can multiply by 2. 24 to 48, we multiply by 2. So it would be our next step here. Would be our next. What? Multiply by 2. 48 to 2 would give us 96 there. Now, if we look at our last table, it's not linear because to get from 8 to 11, I have to add 3. But to get from 11 to 10, I have to subtract 1. So I'm not adding or subtracting the same thing each time. It's also not exponential because I can't multiply by the same thing each time either. To get from 8 to 11, I have to multiply by 1 point something. But then to get from 11 to 10, I would have to multiply by something less than 1. So it's not linear, it's not exponential, but that doesn't mean there's no pattern here. So I want to take a look at what happens when I dig a little deeper on how these values are changing. So to get from 8 to 11, we said we have to add 3. Then to get from 11 to 10, I have to subtract 1. To get from 10 to 5, I have to subtract 5. To get from 5 to -4, I have to subtract 9. So these are all different. Again, it's not linear, but if I look at these numbers, there's a pattern here. To get from 3 to -1, I would have to subtract 4. To get from -1 to 5, I would subtract 4. And to get from 5 to -9, I would subtract 4. These numbers, while different, do have a pattern. So if I wanted to find the next term, I'm not sure exactly what it is I'm going to subtract, but I could figure it out. I know that whatever this number is going to be 4 less than 9. Not -9, 4 less than -9. -9 minus 4 would give us -13. So that means I'm going to take my last y value and subtract 13. So -4 minus 13 gives me -17 for my next y value. This is a new pattern. This is different than what we've seen so far. This is a quadratic function. Questions for me so far? Okay, so let's look at a couple options of our functions that we've seen so far. So we have an example of a linear, an exponential, and a quadratic function. You could sort of think of these patterns like a table of values, or we could take a look at how we change those y values each time. So for our linear function, to get from 0 to 2, I have to add 2. To get from 2 to 4, I have to add 2. So what would be our next number? 6, then 8, then 10. Good. The other way that we could think about this is if I had a table and I plugged in 0 for x, 2 times 0 would be 0. If I plugged in 1 for x, 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is 8. And we could do the same thing for our exponential function. So 1 times what gives me 2? 2, yeah. And then 2 times 2 gives me 4. So what's the next number? 4 times 2 gives me 8, then 16 and 32. Very good. And again, if I wanted to, I could think about this as an XY table, right? For an x value of 0, if I put in 0 for the exponent here, I would get 1. For an x value of 1, 2 to the first would give me 2. 2 squared would give me 4. 2 cubed would give me 8. 2 to the fourth gives me 16. And 2 to the fifth gives me 32. So if I wanted to use my function, I could use my function as well. Now for a quadratic function, we're looking at something like this, x squared. So if I looked at that pattern to begin with, to get from 0 to 1, I have to add 1. To get from 1 to 4, I have to add 3. So what do you think we would add the next time? 5. I want to add 5. 4 plus 5 would give me 9. Now to get to the next term, I would have to add 7. 9 plus 7 gives me 16. Now for the next term, I would have to add 9. 16 plus 9 gives me 25. The other way that we can think about it, if we treat it like a table of values, an XY table, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. That makes sense? So this is what we're going to see, these quadratic functions. Questions for me so far? Okay, let's take a look at the next page. So on page 2, we've got some more patterns that we're going to look at here. We're going to look at a couple together to start. We want to decide for each of these patterns, what are the next few terms? And then is this a linear, exponential, or quadratic pattern? So for A, I've got -10, -12, -14, -16. What am I doing here? It's linear, and I'm subtracting 2 each time. This is a linear pattern. And what are the next few terms going to be? -18, -20, -22. Good participation today. Loving this. Okay, for B, Same idea. What's this pattern? So to get from 10 to 13, I add 3. To get from 13 to 18, I add 5. So it's not linear. To get from 18 to 25, I add 7. Do I see a pattern in these numbers? It's going to be quadratic because these numbers have a pattern. If I checked exponential, I can't multiply 10 by the same number to get 13 as I would have to multiply 13 by to get 18. I can't multiply by the same number each time. This is going to be quadratic. What do I want to add to get the next term? I want to add 9. So 25 plus 9 will give us 34. What will I add next? Add 11. That gives us 45. And then I'm going to add 13. And that gives us 58. I want you now to try C and D. What's our pattern for C? We're dividing by 5 each time. When we were writing exponential functions, we always had to write it as multiplying by something. So for our exponential functions, we just finished that unit, we would think about it as multiplying by 1/5. But since I'm just asking you to continue the pattern, dividing by 5 works just fine too. So 100 divided by 5 gives us 20. 20 divided by 5 gives us 4. I'm not going to get whole numbers for the rest of our terms, but that's okay. So 4 divided by 5 would give us 4/5. If you did 0.8 instead, that's fine too. If I divide by 5 again, that would be 4/25. Then if I divide by 5 once more, that would be 4/125. Again, if you wrote decimals, that's fine too. So what type of pattern is this? Exponential. And then for D, what are we doing here? Anybody determine what type of pattern this is? This is another quadratic. It's not linear because I can't add the same thing each time. I would have to add 7 here and then add 4 here, so not linear. I also can't multiply by the same thing each time. I would be multiplying by 1 point something, a little less than, 1.7, a little less than 2 here. But to get from 22 to 20, I would have to multiply by something less than 1. So it's not exponential. So let's take a look at this. So to get from 10 to 17, we're going to add 7. To get from 17 to 21, we add 4. 21 to 22, we add 1. 20 to 20, 22 to 20, we're going to subtract 2. How are these numbers changing each time? We go down by 3 each time. So I have to subtract 3 each time. So the next number would be -2 minus 3. So I'm going to subtract 5. That would give me 15 here. And then I would subtract 8, giving me 7. And then I would subtract 11, which would give me -4. Questions for me on the first example on page 2? Okay. Now let's look at a couple patterns that have a visual representation. So if we look down at example 2 on the same page, we've got 2 different patterns here. Draw a little squiggle through them. So here's our first pattern and here's our second pattern. We want to sort of make a table out of these first 2 values to see if we can spot the trend here. Is it linear? Is it exponential? Is it quadratic? And then we want to come up with some future terms and a general sort of rule to describe what's happening, a function to describe what's happening. So for our first pattern, step 0 has 1 dot. Step 1 has 3 dots. Step 2 has 5 dots. Step 3 has 7 dots. How many dots do you think step 4 would have? Yeah, we're adding 2 each time. So it's like we add another sort of column of 2 dots each time. So step 5, we would have 11, right? Or if I looked at the values in my table, we're adding 2 each time. What type of pattern is this? This is linear. Now, for step 10, I've got a little bit of a gap here. We talked about this in our sequences unit. One option to figure out how many dots I'd have in step 10 is to figure out how many dots I'd have in steps 6, 7, 8, and 9, and then use step 9 to find step 10. The other option is to come up with a sort of generalized version of this pattern that would let me, it's sort of an explicit formula, like we talked about in our sequences unit, that would let me say, hey, I want the 10th step, so I'm going to plug in 10. So we thought about this as a linear function, since we know it's a linear pattern. I know the slope, I know how I'm changing each time, and I have a point here, so I'm going to write something akin to point slope form. So this would be, for my pattern, 2 times n minus 0 plus 1. So if I want to find the 10th step in this pattern, that would be 2 times 10 minus 0 plus 1. 2 times 10 is 20. 20 plus 1 would give me 21 dots in the 10th picture of this pattern. You're going to figure it out? Okay. Now let's do the same thing for pattern 2. So for pattern 2, our step 0 has 0 dots. Our step 1 has 1 dot. Step 2 has 4 dots. Step 3 has 9 dots. How many dots do you think we'll see in step 4? 16. Yeah, our pattern is that we build essentially a square that's tall and wide, however many dots, the like number of steps that we're on. So for step 2, it's 2 by 2. For step 3, it's 3 by 3. For step 4, it should be 4 by 4. For step 5, 5 by 5. So I would expect step 5 to have 25 dots. So essentially, whatever step I'm on, I'm making a square out of that. 2 long by 2 tall, 3 long by 3 tall, 4 long by 4 tall. So for my pattern here, I'm taking whatever step I'm on and squaring it to get that total number of dots. So how many dots would be in our 10th step here? 100. So what type of pattern is this? This is quadratic. And if I looked at those y values, I add 1, then I add 3, then I add 5, then I add 7. These numbers aren't the same, but they're changing at a predictable pace. Questions for me so far? Yes. Whatever step I'm on. So if I wanted to find like the 15th value, I would plug in 15. Does that make sense? Okay. Okay. Turn to the next page for me. We have a couple more that we're going to look at. So we've got a new pattern on the top of page 3. We're looking at the same thing. Okay, we have the same goal. Step 1 has 3 little squares, little blocks here. Step 2 has 6 blocks. Step 3 has 9, 10, 11 blocks. So first, let's draw what we think step 4 would look like. Yeah, exactly. With these visual patterns, I like to pick out where the squares are. I think that makes it a little easier to figure out what's going on. So if I look at step 2, I can see that 2 by 2 square here. If I look at step 3, I can see that 3 by 3 square here. And then for step 1, that guy in the middle could be my 1 by 1 square. So for step 4, I'm going to have that 4 by 4 square in the middle. And then I've got 1 on each end at the bottom. That would give me, this would be 16, 17, 18 blocks. So I want to know, how many blocks would I have for step 5? What'd you get? 27. I would be another row high and another row wide. If I look at my y values, I can see I'm adding 3, then I'm adding 5, then I'm adding 7. So we would need to add 9. Now, for the next couple of values, we have a jump again. So it would be helpful to have that sort of explicit formula. We think back to our sequences unit. I want some sort of way to describe what's happening. So if I think about the squares that I've got here, this is 3 squared and then plus 2. Here I've got 2 squared plus 2. Here I've got 1 squared plus 2. Our 4 was 4 squared, right? 4 by 4 plus 2. So if I wanted a formula for this, whatever step I'm on, square it and add 2. So n squared plus 2. That lets me a little more easily find the number of blocks I would use for step 10 and step 12. How many blocks would I use for step 10? 102. 10 squared is 100 plus 2. How about step 12? Yeah. 46. Yep. 12 squared is 144 plus 2 would be 146. What type of pattern do we have here? A quadratic pattern. Okay, let's jump down to example 4. Same idea. We're going to go through the first couple together, and then I'm going to ask you to try it. So I want to write a formula for our quadratic patterns. We know these are all going to be quadratic. We want to write the formula for them. Just like we did with our last example, I'm going to try where we have these visual patterns to find the squares. So if I look at A, a lot of times the squares are easier to find with steps 2 and step 3. It can be a little tricky with step 1. But if I look at step 2 for A, I can see the square here. I can see the 2 by 2 square. So this would be 2 squared plus 1. For step 3, there's my 3 by 3 square. So I've got 3 squared 1 again. If I go back to step 1, we'll call this our 1 by 1 square, and then I'm adding 1. So it would be our general pattern here. N squared plus 1. Good. Now let's take a look at B. Same idea. Yeah. So do you see where my squares are here? But it's not just 2 squared, right? I've got this 1 that I'm adding to it. Yeah. Does that make sense? Okay. So for B, same idea. I want to find the squares. That looks like a 2 by 2 square to me. So I've got 2 squared plus 2. For step 3, there's a 3 by 3 squared. So I've got 3 squared plus 3. If I look at step 1, I'm going to call that my 1 by 1 square plus 1. A little bit different on this one because we're not adding the same thing to our square each time, right? As our square grows, so does what we're adding. But I can predict what I'm going to add, right? Exactly right. N squared plus n. So whatever step I'm on, what I add, that sort of extra column of blocks, is going to be just as tall as my square. I want you guys now to try C and D. So you're trying to write that pattern, that expression, I should say, for your pattern. What did we get for C? N squared plus 2. Here's my 2 by 2 square plus 2. Here's my 3 by 3 square plus 2. You could think of this as my 1 by 1 square plus 2. N squared plus 2 for each of those. And then how about D? N squared plus 4. So there's my 1 by 1 square. Here's my 2 by 2 square. Here's my 3 by 3 square plus 4 each time. Questions for me for today? Okay, we're going to stop there for today. On Monday, we're going to talk about graphs of quadratic functions. Now that we know what those patterns look like, how they're different from linear and exponential functions, we're going to take a look at what the graphs of quadratic functions look like. That is it for today.